So let us begin discussion on DPPs. This is DPP1 on phase diagrams and lever rule. To make stronger jewelry, use as pure gold as possible. As we discussed in the class, that the pure material will not be strong. Pure material will not be strong, and alloys are always stronger than the pure metal. So when we go to the jewelry shop, we see 22 karat gold. In the jewelry shop, it is also written 916 kdm. This is nothing but cadmium. And how this 916 came? 24 karat gold is 100% pure gold. So 22 divided by 24 into 100 comes out to be 91.6%. So to make the gold stronger and to make jewelry, you have to add either copper or cadmium. Previously, we used to add copper, and technically copper is a very good impurity. Now we add cadmium because reprocessing the gold becomes easier when we have cadmium in it. So 91.6% gold is called 916 kdm, means with the remaining impurities are cadmium. So 100 minus 91.6 means 8.4% impurity. So 8.4 impurity. And sometime to make a stronger jewelry, we add more impurity. Either we use 20 karat jewelry or we say 22 karat jewelry. In foreign countries, you will get 16 to 18 karat because they want to make the jewelry more stronger. So answer is C. Add approximately 8.4 to 16.8% copper or cadmium. Sometimes cadmium reacts with the body and the body becomes a little black wherever you are wearing the jewelry. But anyway, when we reprocess gold, when we heat the gold, cadmium will vaporize and you will left with the pure gold. Removing copper from gold is difficult during the reprocessing. That is the reason we add cadmium, not copper. Now the diamond jewelry will be made in. Diamond is much more stronger than any other material. Diamond is very hard. So suppose there is a finger ring made up of diamond, but the base will be gold, na? So to hold diamond, gold must be stronger. So diamond jewelries are made in lesser grade gold, means 18 karat gold. You add more impurity so that the gold becomes more stronger. But certainly we cannot go less than 50% impurity. Because less than 50% impurity, the impurity atom will become the base metal and the strength of impurity atom will dominate. So diamond jewelries are made in 18 karat gold because diamond is much more harder and stronger. Graphite to black diamond transformation can be seen in. This is the pure substance. Graphite is a pure carbon. Diamond is pure carbon. So pure carbon to pure carbon transformation takes place on a unary phase diagram because this is the temperature versus pressure diagram like this. So here you will get black diamond. Like whatever you study in thermodynamics pure substance, like PV diagram, TS diagram, HS diagram, they are all unary phase diagram. Unary phase diagram. In other words, number of component is 1 in the Gibbs phase rule. In the Gibbs phase rule, when the number of component is 1, it means it's the diagram of pure substance. So graphite to black diamond transformation takes place on a unary phase diagram. It's MSQ. Eutectic phase diagrams are ones where eutectic point appears. So if you see the phase diagram, like it's a partial solid solubility, na? Here there is a 100% A, and here there is a 100% B. So B alpha is a partial solid solubility of B in A. Beta is a partial solid solubility of A in B. So wherever there is a partial solid solubility, you will get the eutectic point. This is the eutectic point. And at the eutectic point, there is no meshy zone. So eutectic point appears, then that diagram is called eutectic phase diagram. See, this complete solid solubility is nothing but isomorphism. Isomorphism. So that is not the right solution. Partial solid solubility of two material, that is also correct. Complete insolubility. See, when there is a complete solid insolubility, then there will also be eutectic point. This is the diagram of complete insolubility: liquid plus A, liquid plus B, and A plus B. This is also complete insolubility. There also eutectic point appears. But option D is complete insolubility, means complete insolubility in the liquid as well as in the solid state. So when there is a complete insolubility in the liquid state, there is no phase diagram. When there is a complete liquid insolubility, then there is no phase diagram. So that is the reason I am not taking D. But suppose if it is a complete solid insolubility, then I will put it correct. Got it? So the answer will be A and C. And if it is a complete solid insolubility, then I would have taken D as well. Okay? The best solder alloy is a lead and tin alloy. Percentage tin, alpha, beta, and we know that this is 62% tin. So 62% tin, rest will be lead, 38% will be lead. This will be the best solder alloy because its melting point will be minimum. And there is no mushy zone. So B. So at much lower energy, that material will melt out and we can paste it wherever we want, any electronic circuit. So why best solder alloy? Best solder alloy because its melting point is minimum. Okay. So the stainless steel, the way chromium provides corrosion resistance. Chromium provides the corrosion resistance. So the way I have taught in the class is, suppose there is a grain boundary. Chromium, after reacting with atmospheric oxygen, produces Cr2O3. And being the foreign element, so any foreign element, where it will be accumulated? At the grain boundary. Any foreign element will be accumulated at the grain boundary, because interstitial spaces are slightly more. So at grain boundary, bond length will be slightly larger. Larger the bond length, easily bond can break. That's the reason corrosion always starts at grain boundary. But what the Cr2O3 has done, it formed a protective layer over the grain boundary, preventing the grain boundary atoms from the attack of atmospheric gases. So B. It doesn't produce surface coating of Cr2O3 over the surface. That is not correct. Okay. So it produces protective layer at the grain boundary, because grain boundary atoms were the first one to be attacked. Single crystal superalloys are used in the steam turbine. See, this question appeared in GATE 2023. GATE 2023. Sorry, engineering services. 2023. So why we use single crystal superalloys in steam turbine? Because grain boundary at high temperature, grain boundary atoms are having tendency to flow. So to have a decreased creep, we use single crystal alloy. Single crystal alloy are used to decrease the creep. And how they are manufactured? By casting under a controlled atmosphere. Coring or miscibility gap appears in copper nickel alloys when, see, if you see copper nickel phase diagram, it is like this. So when we cool rapidly, this we have discussed elaborately in class. When we cool rapidly, then at point D, within the grain there will be concentration gradients. And at the grain boundary, percentage nickel will be less. At the grain boundary, percentage nickel will be less. And what we can see from the copper nickel phase diagram, lower is the percentage of nickel, lesser will be the melting point. See, lower is the percentage of nickel, lower will be the melting point. So at grain boundary, melting point will be low. So if you hot work the material, grain boundary material will melt out, producing crack that leads to brittle fracture. This phenomena is called coring or miscibility gap, and it happens when we are cooling the material very fast. I hope you enjoyed the first DPP.